So in the last video, we talked about linear difference equations. In this video, we're going to specialize down to first-order linear difference equations, which are the simplest non-trivial examples of linear difference equations. So let's consider the A first-order linear difference equation in standard form. Difference equation x sub t plus 1 is equal to a sub t x sub t plus b sub t, where those are all reals. So clearly, if we have an initial condition x naught, so given initial condition x naught, this has a unique solution by just iteratively applying the recurrence relation. If you do that, you'll find that x sub t plus 1 is equal to the product over I equals 0 to t of our a sub i's times x naught, our initial condition, plus b sub t plus the sum from I equals 0 to t minus 1 of b sub I times the product for j from I plus 1 to t of a sub j. Now this is a little bit ugly, but it does give us an explicit formula for computing the x sub t plus 1 given the previous entries, x sub t. But now, it turns out that if our a's and b's are constant, then we get a geometric series, and there's actually a very nice closed form formula for it. So suppose a sub t is equal to a, and b sub t is equal to b, and these are constants. Then, well, plugging those in, we get x sub t plus 1 is equal to ax sub t plus b. And plugging that back into our solution, we get a geometric series, and so x sub t plus 1 is equal to a to the t plus 1 x naught plus b times the sum over I equals 0 to t of a to the I. And of course, this has different values depending on whether or not a is equal to 1 or not. So we conclude that x sub t plus 1 is equal to, let's rewrite this, x naught, a to the t plus 1 plus b times, well, we're summing up the geometric series, 1 minus a to the t plus 1 over 1 minus a for a not equal to 1, and x naught plus t plus 1 b for a is equal to 1. So that's a very nice closed form solution if we have constants a and b. Now we won't always have constants a and b, and then for higher order recurrence relations or difference equations, it's going to be hard for us to often explicitly solve for these things. So instead we turn to some solution techniques that you may recall from your differential equations class. In particular, let's quickly prove the principle of superposition, which should be extremely familiar. So the principle of superposition. Suppose we have a function, let's call it x sub h comma t, which satisfies x sub h comma t is equal to a x sub h comma t. Oh, sorry, t plus 1, ax sub h comma t. So the h here stands for homogeneous because it's a solution to the homogeneous equation. And suppose we have another function, x sub p comma t, that satisfies x sub p comma t plus 1 is equal to ax sub p comma t plus b. So this is a particular solution, which is why we you denote it with the index p. Well then, clearly, x sub t is equal to x sub h comma t plus x sub p comma t satisfies x sub t plus 1 is equal to ax sub t plus b by linearity. Okay, and you can just substitute things in and you'll see that this is true. And this turns out to be true for higher order linear equations as well, as we'll see in the next section. But now that we have the principle of superposition, we can do clever things, like solve for the homogeneous system and then just maybe guess a particular solution, and allows us to get a general solution for the original problem. And this here is what we call the method of undetermined coefficients, which you should also recall from the differential equations, since we did something almost identical to solve differential equations with linear coefficients. So method of I can't spell. There. Undetermined coefficients. Method of undetermined coefficients. So now, note that x sub h comma t, if we set that equal to ca to the t, this solves the equation x sub h comma t plus 1 is equal to ax h comma t for all real numbers c. And that you can just see by plugging it in, and it's also something we discussed in the previous video. So now this gives us a solution to the homogeneous equation. All we have to do now is find a solution to the particular equation. So we need to find x sub p. So I am going to guess that xp is equal to k for some constant k. And this is our guess because our coefficient our b value is a constant, and so our initial guess should be that there is some particular solution that's also a constant. We'll see later some other ways of doing this educated guessing. For those of you who are physicists, you may have heard the term ansatz, and this would be an ansatz for the form of the solution. So now, if a is not equal to 1, this works. And we get that k is equal to k plus b, which implies that k is equal to b over 1 minus a. However, if a is equal to 1, this doesn't work so well. So instead, we do a different guess. We guess that xp is equal to t times some constant. You should recall that you made a similar type of ansatz in differential equations whenever the constant guess didn't work for some reason or another, usually related to the eigenvalues of the characteristic polynomial, which we'll cover later when we talk about higher order equations. But in this case, if a is equal to 1, it doesn't work, as you can see here, because you end up getting that k is equal to infinity, which is clearly not a normal real number. But if we guess that xp is equal to tk, well, that does work. So then here we have that t plus 1 times k is equal to tk plus b, which implies that k is equal to b, and xp is equal to tb. So putting that together with the homogeneous solution, we get, x sub t is equal to ca to the t. Let me rewrite that. Ca to the t plus b over 1 minus a. This is if a is not equal to 1, and c plus tb if a is equal to 1. So this solves x sub t plus 1, which is equal to axt plus b. And this here is a general solution, because we have an arbitrary constant c that is still in there. So now, if we were to set the initial condition to be x naught, we actually recapitulate the original result we found by direct substitution further up here. Okay, so now we've seen a couple ways of actually solving for it. It turns out that there are other ways of analyzing the behavior without actually explicitly solving for the solution analytically. And one of these is known as cobwebbing. Why it's known as cobwebbing? Well, that will become clear in a later section, since it's not so clear right now. But it's as this method is most useful for nonlinear difference equations later. It's basically just a graphical plot of the behavior of x sub t as time goes forward. So now suppose that we have x sub t plus 1 is equal to f of x sub t, where f, and this is a first order equation, and I won't write it as a linear first order equation because this method is actually general and works for nonlinear first order equations as well. Let's say that the function y is equal to f of x is the reproduction curve. Reproduction curve. Then cobwebbing is just a matter of performing the following algorithm. So perform the following steps. Algorithm. And you can do this by hand, but we will also be discussing doing this by computer, since it turns out that these sorts of steps and the sort of graphing is often a lot easier with computer assistance. So the first thing we'll do is let's graph the lines y equal x and y equal f of x. Then we're going to let our initial points, let's call them a, b, just for now, be equal to x naught and 0, be the starting point on our diagram, starting point on the graph. And then we repeat the following indefinitely until you get tired of drawing, or your computer gets tired. So repeat the following steps. While moving to the new AB. And drawing a line between the old AB and the new AB so you can see the trajectory. So the first thing you do is you set B equal to f of A. And then the next step is really simple. You set A equal to B. And so this algorithm is helpful in illustrating the behavior of first-order difference equations by graphing the state history. And that's something that we'll see in the problem sessions, as well as in the second half of this lecture, where we'll actually step through the steps of cobwebbing for a simple equation. Thank you very much, and I'll see you in the next video.